In this tutorial, we are going to be talking about buckling load factors, buckling shapes after a Nastran analysis. We're going to be using the Postprocessor web app to look at this data. Now, the Postprocessor web app is free as long as you are an MSC Nastran user. If you're a student or professional engineer and you're using MSC Nastran, again, this web app is free for you to use. Also, the web app, or rather the Postprocessor web app, is only compatible with MSC Nastran. It's not compatible with any other Nastran out there on the market. Now, if you want to download your own version of the Postprocessor web app, you can go to theengineeringlab.com. In the top right hand corner, there's a button that says free download. Click that button, fill out the form, and we'll work with you to get your own installer of the Postprocessor web app. Now, let's go ahead and start this exercise. Click on tutorials and users guide. This will go ahead and take you to this table, Postprocessor tutorials. Now let's go ahead and go to this tutorial called buckling load factor of a thin wall cylinder. Let's go ahead and click on link. And when we do this, we get a zip file, and then inside are the bulk data files and the H5 file for this exercise. The bulk data file contains the mesh, the loads, the materials for that Nastran model. The H5 file contains the results of the Nastran analysis. So in this case, it's a buckling analysis. So we have buckling shapes and we have buckling load factors stored in this H5 file. So if we go back to the home page of the web app, let's go ahead and click on Viewer. Let's click on File Upload. And let's inspect this model real quick. So here are the various elements we're working with. If you want to hide the elements, or if you want to hide the element edges, here, if you click on Display Wireframe, click this blue button, and this will hide the element edges. You can turn them on again by clicking the button. If you want to look at the detail or the thickness of these elements, here in these last two columns, click on these checkboxes. And then if you zoom in, you get an idea of what the thicknesses look like for these various elements. So let's go ahead and turn off all of the thicknesses. So now we're left with the elements here on the screen. One other thing worth mentioning, when you click on first person here on the top left and you click enter controls, you can navigate the model like you would a video game. You can move left and right, you can move forward and out, you can move in and out, you can use the mouse to look around like you do in a video game, you can rotate left or clockwise and counterclockwise. This is very useful if you're dealing with a very complicated model. This could be an aircraft system. This could be a ground vehicle. You need to be able to move through the elements and see what's happening within the model. Let's go ahead and exit first person mode and go to the FEM label tool. Let's go ahead and maybe turn on the displacement coordinate system we're working with today. The degrees of freedom for these nodes are defined by this cylindrical coordinate system. Normally, here in the bottom left, we have the so-called basic coordinate system. For those who are still students, sometimes you would call this the global coordinate system. Normally, your degrees of freedom are parallel to the basic coordinate system. So here as an example, here in the bottom left, the x-axis often represents the first degree of freedom. The y-axis represents the second degree of freedom. Then the z-axis represents the axis that goes in and out. But here we're using a cylindrical coordinate system for the degrees of freedom. Here in the FEM label tool, there's a button called Display Displacement Coordinate Systems, or the degrees of freedom. When you do that, you then get axis helpers for each node. These axis helpers represent the degrees of freedom for that node. And you can see one characteristic for this example. let me go ahead and do this. Let me see if I can turn off this and this. Let's go ahead and change the colors. It's a little easier to look at. So here in the middle is our cylindrical coordinate system. You can see that the first degree of freedom for each node is radial. So here you can see if you follow a path from the origin of the coordinate system to the node, you can see that the first degree of freedom is radial. And then the second degree of freedom, you can think of it as like a tangential degree of freedom. And I should be careful here because let's say we walk out some radius and then we rotate. You can see that as we rotate here from here, at almost like a tangent, this defines the second degree of freedom for each node. But you can see a difference here. When we're at this node, the second degree of freedom appears vertical here. But now let's suppose we're here. The second degree of freedom, which is a green line, is now horizontal. So this is what I mean, that the degrees of freedom depend on where you are at in this coordinate system. So you can see first degree of freedom is in this direction, but then the second degree of freedom kind of depends on where you're at in space. Now, this is very important when we talk about the eigenvectors, which we'll get to in a few moments. Now, let's go ahead and upload the bulk, or not the bulk data file, but the H5 file that contains the buckling load factors and the buckling shapes. So here we get a plot, and the first thing you'll notice, we don't get that colorful rainbow plot, which is called the fringe plot. This is because I'm hiding the colors of the element faces. So let's go ahead and go back to the model display panel. We'll go ahead and display those colors. And now when I go back to the post processor, I should be seeing some colors. Now, the buckling shape looks really off, and that's because the scale factor is really high. So maybe let's bring that down to maybe 1. And maybe let's use 2. Just so it's a little bit more noticeable. So this is the first buckling shape. And when we look here, we get some information. We get told that the eigenvalue is 2.69. So let's go ahead and do this. So the eigenvalue, or the buckling load factor, that is equal to 2.69. So what is the buckling load? So this is going to be the load times the BLF. The load is 100. If you look in here, if you look at the P-load 4 entries, you can see that the pressure is 100 for the most part. So that's why I'm taking 100 here as the load, and then I'm multiplying it by the buckling load factor, which is a 2.69, which gives me a value of about 269 psi. So let's go ahead and add some units here. And now this exercise, if I have not mentioned this before, this exercise is actually from the Patran post-processing manual. If you look in problem 17 titled Buckling Shells and Cylindrical Coordinates, you'll find more information about the analysis model that we're working with today. Now, what I'm looking for is this table. So we get one row that tells us the theoretical buckling load factor. So here we get told that the buckling load factor from theory is about, let me go ahead and paste that here, 256 psi. So you can see there's some small difference in the results, which is okay. Finite element is an approximation. I'm sure if we use a finer mesh, we'll get closer to that actual buckling load. So now, this is the buckling load. We took the buckling load factor, which was 2.69. We multiplied it with the load. Now, sometimes when you work with buckling load factors, you might get a buckling load factor that's negative. So you might be asking, okay, what happens when I get a negative buckling load factor? My professor never ever mentioned about a negative buckling load factor. So it's the same equation as before. It's the load times the BLF. So here it's a 100 psi times negative 2.69 psi, or not psi, but negative 2.69 is the eigenvalue or the buckling load factor. So what does this mean? we get negative 269 psi. So this is telling me that I get buckling at negative 269 psi. Or if I were to reverse the load, then I get buckling. That's what a negative buckling load factor means. I might repeat this later on, but I wanted to point this out because it's a very commonly asked question. Now, let's go ahead and talk about the different buckling shapes. So this is a buckling shape 2. I know this is buckling shape 2 because if we look at the table, there's a column called mode. So this is buckling shape 1, buckling shape 2, buckling shape 3, buckling shape 4. Some might call it buckling mode 1, buckling mode 2, 3, and 4, and so on and so on. This is what buckling mode 4 looks like. And here you can see the eigenvalue is higher, it's 5.9. Let's see. Let's talk about eigenvectors for a quick moment. Let's go ahead and go back to buckling mode 1. And right now we're looking at the magnitude of the eigenvectors. Let's go ahead and do this. Let's display only the x component for the buckling, for the eigenvector or the mode shape. So let's turn it off and on, off and on. So you can see these nodes are moving along the x-axis in the basic coordinate system. So you can imagine if there is an observer here at the basic coordinate system here in the bottom left, you told the observer, hey, I want to look at your perspective when it comes to the x component. So that's why we have the nodes moving in horizontally, essentially. So this is the before and after with the eigenvector. What about the y component? What does that look like? So I believe this would be a vertical change in the eigenvector. So here you can see that the nodes are moving vertically. But we want to look at these results from the degrees of freedom or the displacement coordinate system. So here what we're going to do is we're going to change the coordinate system to the cylindrical coordinate system. And look at what's different now. Let's go ahead and look at the x component. Let's go ahead and turn this off and on. So before, the nodes were moving along the x direction of the basic coordinate system. But if you remember when we looked at the degrees of freedom here, the first component from the cylindrical coordinate system is radial. So when we look at the results using the first or the cylindrical coordinate system here, you can see that the nodes are now moving radially. And that's what I wanted to point out, that this coordinate system option controls the which observer you're viewing the values from. You can either view the values from the cylindrical coordinate system, or you can view the values from the basic coordinate system, as you saw here a moment ago. Okay, then what else is there to cover? Some of you might have a need to write out the buckling load factors to a CSV file. So how would you do that? There's another web app called the HDF5 Explorer. Let's go ahead and select that H5 file and upload it. The HDF5 Explorer is used in two ways. The first way is to extract the data and write out the data to a table. So here is a table of all the buckling load factors. So if we zoom in, there's a column for eigenvalue or buckling load factors, so 2.69, 2.81. Here in the top right, you can click download CSV, and then this will download a CSV file for you. And here what you can do, you can select the data and go ahead and create your bar chart. And then you have to take some time to maybe turn off some of the values. So here, let's go ahead and only display this column. Or maybe the wrong column. Let's go ahead and display that. Oh, I got my bearings all mixed up. Let's just go ahead and do this. So these, I believe, would be the eigenvalues versus modes. And oh boy, this is actually a lot more difficult than I was expecting. But that's okay. There's still some more work to do to create your bar charts. The second thing the HTML5 Explorer can do, it can create the graphs for you automatically. So I think you saw how I was starting to struggle to create this bar chart in Excel. If you are someone that spends hours trying to create graphs from Nastran results, I definitely recommend you consider using the HTML5 Explorer. Here's the same graph that we were looking at a moment ago. Here along the horizontal axis, we're looking at the various mode numbers. And then here on the vertical axis, we're looking at the eigenvalues or the mode shapes, or sorry, the eigenvalues or the buckling load factors. If you want to, you can also download this table to a CSV file. And so here are my 4 buckling load factors. I don't know if this will work, but let's see if it does work. Let's go ahead and create a bar chart from this. So this looks a little better. We still have to spend some time formatting this. So again, if you're ever someone who spent hours with Excel and a text editor trying to create your graphs, definitely consider the HTML5 Explorer. It's a lot faster. So I think we're pretty much at the end of this exercise. As a quick reminder, the Postprocessor web app and the HTML5 Explorer, they're free as long as you're an MSC Nastran user. It's only compatible with MSC Nastran. This is not compatible with other Nastran versions. You can visit theengineeringlab.com, click on free download on the top, fill out the form, and then we'll work with you to get you your own installer for the Postprocessor web app. With that, thank you so much for watching.